We shall start our discussion today on condenser, and then we will try to discuss about second law of the steam power cycle. In the last class we have discussed about steam generators, that is boilers, and we have seen the classification of different types of boiler and the problem associated of each type in the context of the operation of the steam power cycle. So, today we will discuss about condenser first, and then we will discuss about the second law. So, if we draw the, so this is boiler, then steam is expanding and after doing work steam is taken to this so this is W in, this is Q in, so this is 1, 2, 3 and 4. So, this is Q out. Now, question is, we have discussed about the power cycle first, then we have discussed about turbine, and yesterday we have discussed about the boilers, that is steam generators. Since this is not included in this course, so although I am very much sure you have studied about pumps in fluid machinery course, and today we shall discuss about condenser. So, first of all, if we try to discuss about the necessity of having this equipment in this cycle. So, condenser utility. If we look at this diagram, we can see that this condenser is an important component for this cycle. Now, what is the need of condenser? We know that we are supplying heat into the boiler, and upon receiving heat water is getting converted into steam, and that steam is allowed to expand in the turbine, and from there we are getting work output. Remaining steam, I mean after doing some work, steam is allowed to go through the condenser, wherein we are having heat rejection. So, question is, we are supplying heat by burning coal or burning fuel. If it is coal fired boiler, then it, I mean if it is coal fired boiler, this energy will coming from the coal combustion. If it is diesel fired boiler, then energy is coming from the diesel combustion. Now, at the cost of that input energy, you are getting some work output, and we have discussed in the last class that the work output is not equal to the heat that is being added into the system, and from there we can classify that work is high grade energy and heat is low grade energy, right, because the amount of heat added into the system is not getting converted equally into the same amount of work. So, we can classify, rather we can grade the energy, that is work and heat, in in different forms. So, what is important that the work output is not equal to the heat input, and some amount of energy is getting rejected in this condenser. So, why do we need to have this particular equipment, knowing fully that energy which is added out of that input energy, that is this energy is coming by either by burning coal or by burning diesel. So, now at the cost of that input energy, if we, why we need to have this amount of heat rejection. So, the condenser utilities that you have studied second law of thermodynamics, second law of thermodynamics puts a restriction that if we need to run the system in a cyclic process, cyclic manner, then if the situation would have been like this, that after getting certain amount of work, steam will be exhausted, I mean in that case we could have expanded steam further, extracting the maximum amount of work, we could have directly discharged that steam into the surroundings, but in that case it would not have been possible to operate the system in a cyclic manner. So, to operate the processes in a cyclic manner, we must have a sink wherein heat should be rejected, and that is second law of thermodynamics. We have studied that it is impossible to construct a engine or device which will operate in a cycle while exchanging heat with single temperature thermal reservoir. So, maybe we are having this source, that is one temperature reservoir from where we are supplying heat into the system. Upon receiving that amount of heat, we are getting work output, but to satisfy the second law of thermodynamics, there must be a heat sink, and that is why this condenser is used. So, the necessity of this condenser is that, knowing fully that we are going to have rejection of certain amount of energy, though that energy was added into the system by burning coal or burning fuel, any other fuel, still we are going to reject this. Why? Only to have the cyclic process. Okay. So, this is the important. Now, question is, today we will briefly touch upon the condenser, because in this course we are not having we are not permitted to have detailed discussion about each and individual component, but I have tried my best to the extent possible. So, if we try to draw the TS diagram, right, and if we draw the vapor dome, now if I draw the process line, so this is say one process, let me draw it, and so this is 1, this is 2, and this is 3, this is 4, right. So, this is the TS diagram, that means we have been able to map the processes which are there in this cycle in this thermodynamic plane. Question is, the process 4-1 is the condensation process. So, this is condenser pressure. So, this is P condenser. Okay. So, now you see that as I told you, so this is basically, if I draw this, so this area is this area in TS plane will essentially signify this is Q out. So, what is, so you see, I mean this is the area which is the W net. So, this is W net. Our objective should be to increase the efficiency of the plant. Now, you know that the 4-1 is the condensation process that occurs at a constant pressure. So, heat will be rejected from the steam. What we can do, our objective should be to increase the efficiency just without going into the physical aspects or physics of this, just if we try to look at the TS plane. So, our objective should be to increase the area that is shown, that W net. So, if we get higher W net, efficiency will be high, because eta equal to 1 minus Q out by Q in, or I can write W net by Q in. So, 1 minus Q out by Q in equal to W net by Q in. So, if we increase this quantity, efficiency of the plant will increase. By how we can increase? So, what we can do, I mean this condensation process is occurring at a constant pressure, that is P condenser. What we can do, we can reduce the pressure at which condenser is operating. Say instead of this, I can have, this is the condenser pressure. So, this is P condenser nu. Okay. In that case, if I try to draw, say this is nu 1 point and this is nu 2 point. So, this is 2 prime. So, this is 1 prime. Try to understand, if we allow the condenser to operate at that pressure, that is P condenser nu, perhaps this is the amount of W net we are getting additionally. Right. So, I have shaded this portion using red color. So, this is the extra amount of work that we will be getting if we allow condenser to operate at a pressure which is less than the previous pressure. So, I mean heat is getting rejected at the condenser. By suitably operating the condenser, we can control the heat or that amount that will be rejected from the system into the surroundings, and we may get higher condenser, higher work output. Since this much amount of additional W net, if we can have, then we can have the higher, relatively higher efficiency of the plant. So, now I will be coming to the question that, see, condenser, we can see that the condenser is a component wherein we will be having heat transfer. Though we can assume that all the processes are internally reversible, but transfer of heat from the steam into the water. So, here water will be circulated. So, this is out, this is in. So, this is out, this is in. So, we are supplying coolant, we are taking coolant, that is water from the nearby lakes, ponds, and that coolant is supplied, I will be discussing today. Now, from that coolant, when the steam is coming out from the turbine, either coolant will be allowed to mix with the incoming steam, so that temperature of the steam can be reduced, and eventually the condensate that will be collected will be pumped back to the boiler. Now, if we have direct contact type, that is condenser, wherein this coolant will be allowed to mix directly with the incoming steam from the exit of the turbine, in that case again we should have a kind of device in which the amount of steam that we are getting out of this getting from the turbine exit, that equal amount of condensate will be pumped back to the boiler, and remaining amount will be transferred or transferred back to the some places. Now, if it is indirect type, that coolant is coming through the pipe and steam is allowed to fall or steam is allowed to pass over the pipeline, I think coolant pipeline, in that case also we will be having heat exchange phenomenon, and because of this we can reduce the temperature of the steam, and that condensate will be again pumped back to the boiler. So, when whatever may be the case, whether it is direct type, that is coolant is allowed to mix directly with the steam, or if it is indirect type, that is coolant is allowed to pass through the pipe and steam is allowed to pass over the pipe, in both the cases we will be having heat loss, and this heat loss is due to finite temperature difference, and it will lead to the external irreversibility of the system. Okay. So, though all the processes are internally reversible, but because of the heat loss here, due to the finite temperature difference, heat gain into the system due to finite temperature difference, these are external irreversibilities. So, when we are talking about to increase the W net, see, try to understand, maybe we will be taking water, it is not necessary that the coolant temperature will be fixed always. If we say the coolant temperature is, so I can consider the coolant temperature is, so coolant temperature is say 30 degree Celsius. So, that means we are collecting coolant from nearby lake, ponds, etc., and I mean again cooling tower will be there to reduce the temperature, but anyhow it is not mandatory that always we should have coolant temperature 30 degree Celsius, but I am taking, and it is also not a bad I mean assumptions. So, if we maintain the coolant temperature at 30 degree Celsius, so if we can ensure that the heat transfer will be due to finite temperature difference. So, steam temperature will be relatively higher. If I allow steam to expand up to this 4 prime, so that means I am allowing steam to expand further and further, so that the steam temperature at the exit of the turbine will be 35 degree Celsius. So, see if I consider T4, so T4 is say 45 degree Celsius, and if T4 prime is 35 degree Celsius, you can see the degree of cooling. So, basically from 45 to 30. So, if I supply coolant which is having temperature 30 degree, so that heat transfer will be due to 45 minus 30. So, 15 degree temperature difference. If I allow steam to expand further, that means I am trying to extract more amount of work output. In that case, temperature at the exit of the turbine will be 35, and that will lead to the temperature difference smaller as compared to the previous case. If we can reduce the temperature difference, we will be having, we will be in a position to reduce the irreversibilities. So, you can see at the cost of that reduction in irreversibility, work output from the system will be more, which in turn will increase the efficiency of the system. Now, question is, problem is, see, if we allow steam to expand further up to 0.4 prime, you can see that corresponding pressure. So, I mean saturation pressure corresponding to this temperature T4 will be even less. Say if it is P condenser in first case, if it is atmospheric pressure, right. So, normally I mean it is taken that condensers are allowed to work below atmospheric pressure. Okay. You can understand the saturation temperature corresponding to atmospheric pressure is 99.99. In that case, I mean if we consider steam, temperature at the exit of the turbine will be 99.9, in that case, if the coolant temperature is 30 degrees, so high degree of irreversibility will be there. So, to accounting for that particular aspect, what is done, condensers are allowed to operate at a reduced pressure, that is at a lower pressure than the atmospheric pressure. So, when we are allowing the steam to expand further and further, so you can see the P condenser nu is again less than P condenser. Question is, if I allow the condenser to operate at a pressure which is significantly less than the atmospheric pressure, chances will be there that air might leak through different parts into the condenser. So, air leakage problem would be there. So, what we can do to summarize, see, we are allowing steam to expand further and further. It is because of this reason we can have higher thermal efficiency, right. But we are also going to invite one problem, that if we allow turbine to steam to expand turbine further, the temperature at the exit of the steam will be say close to 40 degree. In that case, because of this difference in temperature between coolant and the steam exit temperature at the turbine, the degree of irreversibility can be minimized. So, in a way we can get higher work output, but at that temperature the saturation pressure will be sufficiently less, significantly less than the atmospheric pressure. So, when the condenser is operating at a pressure which is significantly below the atmospheric pressure, the leakage of air into the condenser, that problem will be there. So, the designer will be in trouble to design such a component which will be operating at a pressure which is significantly less than the atmospheric pressure. Not only that, the air leakage into that condenser, and that air might that air leakage or air will lead to different problem that I will be discussing. Okay. So, that you have understood. Now, the condenser basically you have understood the purpose. So, let me discuss about the different types of condensers. Okay. Number one is direct type, number two is indirect type. Okay. So, direct type and indirect type condenser, you can see that. So, direct type is spray condenser, that we will be discussing about. Indirect type is surface condenser. Okay. So, indirect type condenser is the surface condenser that I will be discussing today. Okay. So, surface condenser. See, if I go to the next slide and if I try to discuss about direct type. What is done? You know that in this direct type, right. So, we will be having coolant, okay, and steam will be allowed to spray on this coolant, and so this is steam from turbine, and coolant maybe is allowed to pass through this, and this is coolant is coming. Okay. So, you can see coolant is allowed to pass through the pipe in the form of a spray, and steam is coming from the top, and so these two streams will mix together. Okay. So, what we will be getting? So, this is a condenser, and the collected condensate will be pumped back to the boiler right. So, this is state point say I am talking about. Now, since this is direct type, so the coolant will be allowed to mix with the steam. So, the amount of condensate that will be getting is higher than the mass flow rate of working substance in a per cycle. So, we know the mass flow rate of working substance in the cycle, but since we are externally supplying coolant, so this externally supplied externally added coolant will increase the mass flow rate. So, what we need to do? We need to ensure that when it is pumping, the required quantity is going to the boiler, remaining quantity will be taken to the cooling tower. So, remaining amount will be taken to the cooling tower, and from the cooling tower it is called dry cooling tower. So, that will be supplied here. So, this is known as dry cooling tower. Okay. So, now see if it is say 2, this is 3, this is 4, sorry this is 4, not this is 4, okay, and this is 5. Okay. So, see as I told you, the amount of condensate will be collected is higher than the mass flow rate of the working substance for the cycle. As a result, the amount of condensate that will be allowed to go back to the boiler is the mass flow rate of the working substance. Okay. Remaining amount will be taken to the coolant through the dry cooling tower. Why? Because it is the coolant which is coming out, it is not dry. So, as long as if it is allowed to go again through the condenser, then the efficiency will reduce. So, we need to ensure that the coolant before going into the condenser it should be dry. Okay. So, now see understand, in this case one problem is that a special arrangement should be there. So, in this case if we do this kind of energy balance, that is very important to understand at this point of time. So, what is the mass flow rate? See mass balance. What is the mass balance? See, I mean this m dot 2 will be equal to m dot 4, right. So, the amount of condensate will be supplied to the boiler is equal to the steam mass flow rate that is taken into the condenser, and m dot 3 equal to m dot 5, or I can write that m dot 3 equal to m dot 3 equal to m dot 5 plus m dot 2, right, m dot 5 plus m dot 2. We also can write this not in the rate form. So, I can remove this dot term. So, this is the mass balance. Okay. What about energy balance? I can write energy balance. See, if we consider this is H2 enthalpy, this is H5 and this is H3. So, if we do the energy balance applied to this particular component, and we have discussed so many times the steady flow steady state energy equation, then we can write that m 2 H2 plus m 5 H5 equal to m 3 H3. Okay. So, if we do this analysis, we can write what about m 5. Now, we can do this in, so we can write, I mean we can just write in not in the rate form. So, say we are writing, either we can write in the rate form or just not in the rate form. So, if I consider this m 3, that is m 5 plus m 2, and if I plug in this right hand side, we can write m 5 by m 2 equal to H 2 minus H 3 divided by H 3 minus H 5. So, just you take the m 3 over here and do this simple, very simple algebraic step, and you will be getting this. What you know from this equation is that, see, H 2 minus H 3, H 2 minus H 3 is much greater than H 3 minus H 5, right. So, see, H 2 minus H 3 is much greater than H 3 minus H 5. Definitely H 3 will be higher than H 5, but enthalpy at state point 2 and is much high. So, you can see if H 2 minus H 3 is greater than H 3 minus H 5, you can say the mass flow rate of coolant will be much higher than the mass flow rate of steam. So, if we try to have efficient cooling, essentially to increase the system, essentially to allow the system to run smoothly, the mass flow rate. So, m 5 will be much larger than steam flow rate. So, in this mass flow rate of coolant will be much higher than the. So, I am writing mass flow rate of coolant must be higher than the okay. So, this is the conclusion. Okay. Next we talk about indirect type. In indirect type, which is commonly used in most of the thermal power plant, right. So, indirect type is surface condenser, which is rather this type is commonly used in thermal power plant. Okay. If we try to see, I mean since it is indirect type, so just I am trying to draw. Okay. So, steam will be coming from the exit of the turbine, okay, and water will be allowed or coolant will be allowed to pass through the coolant out and this is coolant in. So, this is stream from turbine. So, steam will be allowed to flow over the turbine and will be collecting the condensate and it will be pumped back to the boiler. Okay. So, this is condensate and this is condenser. Okay. So, this is pump and it will go to boiler. So, this is the indirect type. Why it is called indirect type? You can see if I try to write, if I give the arrow. So, this is the water flow direction and this is the direction. So, coolant is coming from the cooling tower, I mean in thermal power plant it is. So, it is also again it is not a case that always it is or always coolant is taken from the nearby lake ponds. There are so many other issues because I mean when coolant is coming out from the condenser, its temperature is very high. So, if you directly discharge that coolant into ponds, nearby ponds, lakes, I mean environmental impact will be there. So, you are not allowed to directly discharge it. Otherwise, what will happen, you know that the animals which are living in ponds, lakes, rivers, they will die. So, from the environmental constraint, you are not allowed to directly discharge this coolant into the lakes, ponds. Instead, what is done? This coolant is taken in a cooling tower and the cooling tower is again a heat exchanger, wherein by supplying air, the coolant is again cooled down and that coolant is that temperature of the coolant is reduced and that is again taken into the condenser. So, this is the scheme. So, now question is in this indirect type, when the coolant is coming into the condenser, it is allowed to pass through the tube and steam is allowed to pass over the tube, and when steam is passing over the tube, by releasing heat it will condense and that is collected in this chamber and this condensate is again pumped back to the boiler. So, this is how this cycle is completed. Question is, you know that you may have multiple pass or single pass. It is very sometimes depending on the capacity of the plant, I mean depending on the mass flow rate of steam that is coming from the turbine, size of the condenser, you may require to go multi-stage or multiple pass condenser, where is coolant will be allowed to pass multiple times. So, I mean it is up to the designer, but the idea is that steam will be allowed to pass over the tube through which coolant is flowing, and due to the because of this heat exchange, steam will release the temperature to the coolant and that heat will be taken away by the coolant, and when steam is releasing heat it will condense and that condensed steam will be collected in this condensate chamber. Question is, as I told you, if I go back to the previous slide, that condensers are normally operated at a pressure which is sufficiently less than the atmospheric pressure. So, chances of air leakage through the condenser is not quite unexpected. So, rather it is expected that air will leak into the condenser. So, when air is getting in to the condenser, then the air film, so when steam is getting condensed over the surface of the, what will happen So, if I take out a particular tube, so if we take, this is the tube and this is steam, right. So, this is coolant, right. You can see that steam will condense and it will form a small drop, right. So, steam will condense and it will form a drop. Now, as I told you that air leakage is quite expected. So, air will leak from the surrounding into the condenser. So, that air what we will do when steam is getting condensed, that air film will create. So, that air will create a film and that film will disturb the transport of heat, try to understand. So, when steam is getting condensed, it will condense in the form of a drop and eventually it will come out, it will be collected in this condenser chamber, but the leakage air that will also try to condense in the form of a film and that film will reduce the heat transfer rate, because air film, thin film of air will not allow the steam temperature to go, to receive that temperature by the coolant from the steam flowing steam. So, I mean what I would like to say that maybe we can operate this condenser at a reduced pressure, but we must be careful that the condenser will be leak proof. So, that air leakage problem should be minimized. It cannot be completely avoided, if it can be avoided, that is well and good, but the air leakage problem should be minimized, and air leakage, this air that will be there in the condenser will create this type of problem. Okay. So, this is all about this indirect type condenser. So, now finally, I will discuss about one important thing, what do you mean by condenser efficiency. So, unlike the other components, so basically we have discussed so many times and we have quantified the efficiency of the plant, thermal efficiency. When we have discussed about turbines, we have quantified the performance of turbine by defining turbine efficiency. When we have discussed about boiler, we have also discussed the efficiency of the boiler. Similarly, for the condenser we can define condenser efficiency. What mean by condenser efficiency? Let me write you. So, condenser efficiency is that let me draw the condenser. If it is surface type condenser, so this is coolant pipe, okay. So, that is stream flow. Okay. So, now see how can we define the condenser efficiency? Try to understand, the coolant is used to reduce the temperature of the steam. So, in the process of this cooling, temperature of the coolant will increase, that is quite obvious. So, I mean can't we write that in this condenser process, so basically we can write the actual temperature rise of the coolant to the maximum temperature rise of coolant. See, just now few minutes back I was discussing about one important thing, that when you are supplying coolant, this condenser, so this is condenser. So, when you are supplying coolant and this device will be operating at a pressure which is less than the atmospheric pressure, that is quite obvious. If we allow the condenser to operate at atmospheric pressure, then the saturation temperature corresponding to that pressure is 99.99, and that means steam temperature at the exit of the turbine should be 99.99. So, when the steam temperature is 99.99 and coolant temperature is 30 degree, so you can see the temperature difference between these two different streams, and as a result of this finite temperature difference, high degree of irreversibility will be there, right. So, accounting for that high degree of irreversibility, the efficiency of the plant will be reduced, right. So, to increase the efficiency in a way which I have discussed, that we can see by looking at this TS diagram without going into that much thermodynamics details, that if I reduce the condenser pressure, we can increase the area, that is W net. Okay. So, if we reduce the condenser pressure, that means I am allowing steam to expand further and further, so that T4 prime will be very close to this coolant temperature. So, lower the temperature difference, lesser will be the irreversibility and efficiency of the plant will be high. Now, we have also seen that if I reduce the temperature, if I reduce the pressure at which condenser is operating, we cannot eliminate the air leakage problem. So, air leakage problem will be there because this is mechanical device. So, air will leak through the glands and also the joints, etc. So, air will definitely leak. So, when air is leaking, when air is getting into the condenser, this problem will be there. So, when steam will condense in the form of a drop and the air which is there due to the leakage, that air will create a thin film, and that thin film air will lay on the tube surface, and this thin film of the air will reduce the heat transfer rate. So, eventually if we design this condenser, that okay, I mean if we design the condenser that this will be coolant in temperature T in and this is T out. Okay. So, we know that maximum temperature rise of the coolant is T out minus T in. So, this is T out minus T in. So, that is the maximum temperature rise, but in reality we will not be able to get this amount of temperature rise of the coolant. Okay. Why? Because the problem due to the formation of thin film of air, heat transfer rate will be disturbed. So, actual temperature rise of the coolant will be always less than the maximum temperature rise. So, basically design T out will never be reached. So, design T out of the coolant will never be reached because actual T out. So, T out actual will be always less than T out maximum, right, because of the poor heat transfer, and as a result of which the actual temperature rise of the coolant will be always less, and if I take the ratio of these two quantities, we can define efficiency of the condenser. Okay. So, to summarize today's discussion, we have talked about condenser, we have seen the necessity of having condenser in a steam power plant, we have also discussed about that by designing the condenser suitably, by operating the condenser at a suitable pressure, we can control the efficiency of the total plant, right. Now, when we are talking about increased efficiency, if I allow the condenser to operate at a low pressure, we are also going to invite another problem of air leakage, and this air leakage problem also will try to reduce the efficiency of the condenser. Okay. So, with this I stop here today, and in the next class I will be discussing about second law analysis of the power cycle, and we shall try to solve one or two problems, and then we will complete this topic. Thank you.